some proofs for solving for electric field. We used Gauss's law and said, well, somehow if we could enclose this line of charge that has electric field lines going off in all directions, including coming out of the page at you right now, going into the page away from you, we would enclose it with a cylinder, okay? Because then it's just convenient. We've got nice, neat right angles here, okay? They're already perpendicular. If you recall what electric flux is going to be E times A as long as electric field and this enclosing surface area are perpendicular to each other. All right, so we went through that proof. The follow-up now is, suppose we had a sheet of charge, okay, and this could be infinitely large, but we know it's been defined as having some amount of charge per square meter, a uniform amount of coulombs for every square meter of this whole thing. All right, so if we want to figure out what that electric flux is, we need to enclose some portion of this. It's infinite, so we can't enclose the whole thing. But if we enclose a portion of this such that these electric field lines will intersect perpendicular to that area, and these electric field lines intersect perpendicular to that area, all right, then we're looking at a situation where we could easily take E times A and just set that equal to Q enclosed over epsilon naught. We want to enclose something, enclose this in some fashion where E and A are perpendicular to one another. Okay. Now, before I do that, let's just take this area, divide it by, divide both sides by area. Okay, we're going to be looking at electric field equals Q enclosed over area epsilon naught. Okay, this has got to be some enclosing area, some Gaussian surface area is what it's called. Here's the suggestion I'm going to make. Let's try a cylinder again. But instead of using the sidewalls, okay, we're going to use the end caps. If you take a look at this here, we've got this surface area here, excuse me, gee whiz, the surface area here that is enclosing this portion of the charged sheet. Okay, so this is basically our enclosed charge that's going to go up here. All right, and if you take a look at how this surface area intersects those electric field lines, okay, notice that the electric field lines are parallel to the sidewalls. Okay, remember E times A perpendicular is what we're looking for. So it turns out that all of these that are along the sidewall, those don't count this time. All right, those were the electric field lines we looked for when we did the line of charge, but now we're looking at a sheet of charge. Sidewall of the cylinder is not going to be part of our enclosing area. Okay. However, if we take a look at the end caps, okay, these electric field lines are perpendicular to the end caps here, top and bottom of the cylinder. So that that makes it so that we just need to know the end cap areas. Now, I could have used a box instead of a cylinder, and then we'd have the end caps at the top and bottom of the box. But either way is fine, because you'll see it in the next couple steps where all we need to know is that this area here and this area here together are the enclosing areas that are perpendicular to the electric field. Alright, so let's take a couple steps here now. If we consider what is this Q enclosed idea, Q enclosed is going to be our amount of charge per square meter multiplied by the enclosing area. Okay, so if you look at that, here we've got a pretty specifically defined enclosing area. It's going to be the area of a circle that we're enclosing some charge on. If you think about what this does for us, sigma is measured in coulombs per square meter, area is measured in square meters. Because remember, what's supposed to go up top here is the amount of charge enclosed, so we should be looking for the unit of coulombs when we do this. Okay, and right down here, coulombs per square meter times square meters, it's going to leave us with coulombs. Okay, so this here is the amount of charge that's enclosed by this enclosing area. Okay, right in here. Now I could call that a circle. I could put in pi r squared right here, but let's just hold off on that for a second and take a look at what's left in this equation. Okay, let's divide both sides. Excuse me, let's divide this by area now, but keep in mind what this area is. Okay, it's just the end caps. The end cap of the cylinder plus the end cap of the cylinder. The surface area of a cylinder is going to be, well, we're going to leave out the sidewalls. Okay, we're not even going to say that part that involves the sidewalls like we did before. We just need to know this area here plus this area here. Okay, it seems like this can be pi r squared plus pi r squared. Okay, they're the same radius, they're the same pi. All right, so we're just looking at the area plus area of the circle. Okay. Oh my. There we go. So we've got this area up top here and this area down below here, enclosing those electric field lines. All right, now notice what we've got here. Areas are going to be the same. All right, this area up top and this area here for a cylinder, those are going to be the same as this area right here. Okay, so if area cancels, now we're just left with a couple of variables here. Electric field equals sigma over 2 epsilon naught. There's going to be the final equation that we would use for an infinite line of charge. Excuse me, an infinite sheet of charge. Pretty sure this is one of the types of problems that you'll end up using on UTexas assignment number 6.